last time. So what we did, we looked at how to create our own client and then integrate that with the actor framework that we have and using the interface that has been defined for that. So, and that's where we stand right now. So that's the reconstructor that we created. So we're going to elaborate on that. And so right now we have kind of two optical models. We have the active optics, which contains the atmosphere and a wavefront sensor, and we have the on-axis GMT, which this one, let's have a look. Do we put the atmosphere on this one? On-axis model. This one also the atmosphere. Okay, so that's interesting because then we could look at the wavefront error we get here and the wavefront error we get on that side and look at before and after correction, for example. So here we should have we should see the wavefront error coming down. Okay. We're going to, before running a simulation, we're going to do one thing. So you see that now we have two loggers, right? One for what come out of the adaptive optics model and one from the on-axis GMT with atmosphere. I have two loggers because we report for both the wavefront error RMS. And they have the same name. So if I were also linking the output of wavefront RMS from the adaptive optics to arrow here, there will be some confusion, obviously. We won't know what to do. But there's a way to create alias name for some output. And that's what we're going to show you now. So if you, like this, you will have a single logger. So we saw that to create new input, we create new input or output, we use empty enum. So we're going to do that also, create a new one. Enum, we're going to use residual. We're going to call it residual wavefront error RMS because it will be after that adaptive optics. It has to implement the UID trait that we can do. So it has to implement that. And we just need to let the compiler aware that it's going to be an alias to an existing output. And we do that like so. After introducing the review ID, we say it's an alias and we provide the original name, which is wavefront error RMS. So it's an alias to that output. So what it's going to do, what the compiler is going to do with that thing, is going to create code for us. And it's going to call the existing, it's going to create a new interface. In that case, it's going to create a new write interface to implement the write trait, calling, going to implement the write trait for residual wavefront RMS, and this inside the write trait is going to call the write implementation for this one. It's going to do all that for us. So, and we just need also to specify for which client. Here is interesting. You see how we implement the write. We specify the empty enum and the client. So the client we're going to apply it, it's the optical model, like wavefront-error RMS, and we need to specify which traits to implement the interface. We just need right here for now. And in fact, build that.
I have a quick question.
Yeah.
So is this alias thing, is that built into Rust, or is this specific to your framework?
It's specific to my framework.
Oh, okay.
It becomes available when you declare that residual wavefront-error RMS derive from your ID. And then you have this option to create alias.
Is the UID, is that also something that you created in your
Yes, it's
framework?
something that I have created, yes. If you remember, that what I was explaining last time is that each MTNOM is a convenient identifier for an input-output, such as you don't really have to specify the concrete type, which is most of the time a vector of precision. Derive your ID will implement a trait called unique identifier, which will define the type for you. And per default, it will put a vector of a 64. But I guess, and then you have to implement the one. But if it's an alias, then it will reuse the traits that have been written already, right? And it compiles. So now what we can do with this new residual wavefront-error RMS is to where our logging, adaptive optics, calibration must be below, AO actor, adaptive optics, log, and AO logging. So I'm going to comment out the AO logs, because we're not going to use that. We're going to use only the logging, which everything here. And somewhere AO actor, you see we have wavefront-error RMS that we are logging. So now we're going to use our alias name, residual wavefront-error RMS. Does that, and we're going to remove the log here. We don't need this one anymore. That should build as well.
Wait, sorry, what did you remove?
So
never mind, I see.
Yes, I removed the AO logging, which was the AO logging and the corresponding actor, AO log, so I did remove it here. It didn't like it. Let me see what I did wrong. Log, emit, AO logs. Oh yes. Result, I have to change that to logs, because there's no longer AO logs. We remove it. Yes. Yes. I on purpose left something that create an error like this. So if you build it, you should see an error. And it's important because to understand also the error we're seeing here. So you see we use residual wavefront-error RMS, and we call the log function on logs like we do an optical model. We have wavefront-error RMS, and so we have kind of the same syntax here, and here it complains, right? So it's important to understand why it complains, because they look the same and why it doesn't work. So, and the nice thing with the Rust compiler is that it usually gives you the solution, the reason why. So if you log, say, okay, method cannot be called on actor optical model due unsatisfied trait bounds. So that usually means that the trait we implement for this, there's something missing. We implement right, but something else is missing. And here he said, doesn't satisfy optical model size. Size is a trait. So it means the following trait bounds were not satisfied. Optical model size. Okay. So what we just need, it means that we are missing. It means that it doesn't know what is the size of this output, because we have not implemented the size trait. The size trait is already implemented for that one. So we can just tell him, okay, here also implement the size trait based on the size also on this one. And that should solve the problem. And it doesn't solve it because there's something else to remove. But it's not a problem, it's something that is still there, we should not be there. Yes, let's comment that for now. At the end, we need to remove, I comment out these two lines. So again, if you in Visual Code, you can do Control Shift A, and you will introduce, you will comment it for Control Shift A. It's on and off. It turns it on and off. Nice. Okay. I think everybody is still with me.
Yeah, I still get an error when I try and compile it. Yeah. It says it cannot find trait size in the scope.
Yeah, I have the same error. So, and again, it's because we need to specify size. And where is size? Size here? Size. Import size in those actor. It says it here, you see, give you the solution. Use those actor size. That's always nice. It's one of the strong points of Rust, that most of the compiler error also provide hints or even the solution. And so, when you say here which traits you want to use, because in the background the compiler is going to write code here and insert it here, and then compile it. If the traits are not imported in the scope, then it will comply. Write has been already imported, but not signed, so that's why. Okay. Yeah, the compiler is almost your coach. You have to trust him and read what he says, and he will and do what he says. When I start writing programming in Rust, I was not understanding most of what I was doing. I was just following the compiler suggestion. Oh, it worked. Okay, and that's the nice thing about it. And so now with that in place, it should build. Okay, some warning, but we can get that.
In my case, when I put the alias, the colors in my editor looks different to yours. So I don't know if there is something that I should load and I did not, sorry, there is something I should import and I did not import it.
Is it compiled for you?
No.
Oh. What
no, but say? I noticed that since you typed it, for example, you put alias and then you have the options name, client, and traits. And then you get the waveform RMS, the optical model, and write for each of them. And in yours, it appears in green, and in mine, it's orange. So yeah, it seems that it's handled in a different way.
It just, what that means is that so in the background, the Rust Analyzer plugin that we have is going to expand and start to analyze the code that is going to be generated by the compiler already and making sure that everything is there. That means that for you it doesn't exist what you're looking for. And when you compile, what happened to you?
Okay,
do you have what version of?
So, for example, one thing that I noticed is that when I started to import the size, as you did, it said that it's an unused import.
Okay.
But
what dose actor version do you have in the cargo2ml, in the manifest?
Let me see. Dose actor. It's 102.
Okay. What version of UID derive do you have?
030.
And what version of UID do you have? 011?
011.
Okay. Well, you're going to have to share your screen and show me your error because
Okay.
there's no reason why it doesn't should work. Like for let's see what's happening to you.
So you see what I'm saying?
Yeah. Can you show me the what do you have? Okay, stop there. The trait unique identifier is okay. Can you go? Derive UID. Can you go down a bit more?
It's really brackets and brackets. Hashtag brackets, alias brackets.
No, I don't think it is. What do I have? Did I wrote? No, it's bracket and parenthesis. That's the problem.
Oh, okay.
I will put that in Slack. Oops.
Okay. Now I think we are. The colors are still different, but now I got a different error. So now I had the problem in line 186.
Yeah. So
I think we are the same page, right?
go up. You still have an error?
Yes, it's still, but now it's on unsatisfied trait bounds.
And what trait one trait is
Here.
complaining about? Yes. If you go to your error and you read a bit more down, you should tell us what
Optical model.
Oh,
Size.
So if you go up, you have to import size.
Here. But
Okay, it is. So go show me the line where we define residual wavefront error MS. Yes, you need traits. You need to after right you have after the right traits put comma size. You need to that tells him to implement. Sorry, inside the column.
here?
No. Sorry. You can look in Slack as well. I think it's in Slack.
Okay.
But just after right colon size.
Oh, okay.
Just that.
Okay.
Voila. And that should allow you to compile it. Okay. So what is Can you go a bit up to such that I can see the full error? The full error, yeah. I think you went too high. Missing alias client. We go a bit down in the code so that I can see the review ID, name, client, place. What is, I can't see what is wrong here. You define you. Why is it that UID is missing? You are using some other places. 69. Yeah, ID. That's incorrect to me. I don't see.
Does the UID need to be in quotes?
No.
It's exactly equal to this one.
Yeah,
Right.
yeah.
Which we used it last week.
Okay, so can you slowly go down in the error report? The thread Can you go a bit down? Yeah, that's everything is okay. I can't see right now why is it complaining? I don't know. Yeah, everything's to be in place. A news import size. How does that? I don't know. Oh, can you show me again the line where you when you define? Can you remove the space after right? Yes, try that. Yeah, that's works.
That-
Oh, well, that's that should okay. I will have to see to accommodate this kind of thing.
Rod, is it really that sensitive that you can't put spaces afterwards? That's a little. I didn't know that.
Only this particular syntax because it's a string. Otherwise, you can put syntax everywhere. But here, what I'm doing in the background, I split the string here based on
It's a parser.
Yes, based on the colon. I wrote my own parser. So suddenly you have a trait which is the name is space size, and you look for that trait which is not size but space size, and then he is confused. So
I
will have
see.
to. Thank you for finding this bug.
No problem.
I will make sure that we can answer. That space before and after will be removed.
There is another, probably a minor question. I saw an advice here in green, and I believe that it's a typo. You see, add output. I think that it's a missing T here, but it's really minor. I think somewhere probably where you are putting your warning message probably, and I think that this is something that we can see that it's your framework.
Yes.
Okay, I will stop sharing, okay, as it's over.
Okay, thank you. Thank you.
I say thank you.
That's useful working together because I discover bugs that I was not anticipating. Okay, I will share my screen again. Oh, no, not that. Sorry. Let me share again.
Had a random question. So the derive and the alias are macros that you wrote, right?
Yes.
How, like, if I wasn't sure I was using it right, how would I kind of look that up somewhere, what the macro does?
Yes. I don't know if I wrote the documentation properly. Let's go explore. Let's go explore. Where? Those actors.
I mean, for example, with this comma thing, like, could I look at the code of the macro and
yeah, so if you go through the documentation of those actors, there's a module called clients where I give some example how to create clients, but also to alias input and output identifier. And here you can see, for example, the correct syntax. But yeah, we make sure that it can accommodate a space because space is so common but that's something I will do. Okay, so now if you run that, run, and we're going to look at the careful run. I'm more interested in looking at the diagram now than the result. Oh, segmentation for, oh yes, I forgot to export GMT modes path equal data. Does it work now? Okay, so it's running. We can look at the diagram and we should see yes, here you see the on-axis GMT and the latitudes all point to the same log now. So we have all this information in the same logger, which is a bit more convenient. And if we look at this one, data, if we look at I don't know if you have a Jupyter notebook, but if you don't have it, it's okay. You can look at mine. If we open the logs, what? Ah, it's cool. Not data, but logs that packet about. Logs that packet, something like that. Ah, yes. And data. Ah, yes. You see now that you have the wavefront error RMS, the segment piston, detector frame, and residual wavefront error RMS. All that in the same file, which is rather convenient.
Mine actually does not have the residual wavefront error.
Okay, let's see what's happening.
Is not expected. Let me try running it again. I might not have saved it before I ran it.
So it's logs.parquet, the file name that we are using here.
I was using data.ip.
Yes, I was using that before, but
okay.
it's logs.parquet. If you want to check, we should have now.
I can't open it, but I will assume that it works, and I'll look at yours.
What happened?
So in the data.ipy notebook, it's logs.parquet. You said
Yes.
that, and I did not do that. Sorry, my bad. There we go.
You see the residual wavefront RMS?
Yes.
Okay, good. So that's something that is quite convenient because I was noticing that sometimes we may have several optical systems to monitor the same properties under different settings, and having several loggers is not very convenient, but having a single file with all the data there, that's nice. So these alias are very convenient. So now that we look at data.ip, we have also the detector frame, which is, as the name says, the detector frame of a camera and this is the one which is on the on-axis GMT. So this is really the frame without correction by the adaptive optics. And so if we look at the last, data detector frame, NP VStack. Yes, so this is going to be always np.vstack. There's something else I want to talk about today, detector frame. What is it going to be the shape of that? Let's remember this. If we put that into a VStack, we look at the shape. What's that? So we have 15 steps, so we want the last one, and reshape it. Okay. So what we see, let's talk about detector frame now. So we see we are logging that, and each time step we have the detector frame, and we have a snapshot frame. So let me explain a bit what's happening, and because what we would like is a long exposure. In general, is what we are interested to compute the performance and the image from. So TEO is always set up such as when you do a propagation through the telescope, and in the optical path you have defined a wavefront sensor or an imager in that case. It's a continuous integration. You add the frame, right? And until you do a readout, a specific function called readout, which reads the frame, and that frame the detector is reset, and then when you continue the next propagation, you integrate again. Okay. So when you carry, where is it? Here, detector frame. What happens is that you read the detector to get the frame, so you reset it. So you get snapshot images, and it's not what we want here. We want really at the end of the simulation the integrated frame, not the snapshot of them. So now I'm going to show you how we can do that in the framework that we have here. So the first thing we're going to do is we're going to commentate that out. So where we log the detector frame, because it's where the reset happened. So that doesn't mean that propagation to the detector doesn't happen. It still happens, and it's accumulated. It's just that we don't get access to it anymore. Okay? And what we want to do, it's really at the end of what the model has finished here, that we would like to read this frame. Okay? And put that in a new logger just for the detector. So the way to do that is to create a new model with the same client. So I want to bring that into this aspect because it's I think a quite useful things to know about the framework here. So the actors are really transient objects that once they are declared here as argument to the model, they are passed into the model. You lose access to them. You cannot touch them anymore. They are in the actors, and they are kind of processed and transformed, and at the end, the actors are destroyed. You don't have access anymore, right? But you still have access to the client. The client still exists because when we define our actors, what we are really passing, like here, for example, when you do a logging clone on the logging client, it's a reference to the client. So that means that we still have the clients, just the actors that all the reference to it disappear, right? And the client is as you say, it's embedded into this two containers, Arc and Mutex, because we're doing parallel programming. So we want to make sure that when the multiple threads access the same client, they do that in the proper order. Okay, just for that. But the client, the important thing, the client, when the model is over here, the actors that all the reference to the client vanished, but not the client itself. So we can again create a new model. So we're going to copy these two lines here. Let logging. I will put that in Slack. Like this, you can take it from Slack directly. Oops. Voila. I put them. So we take these two lines and we put them at the end here. We don't need, oh sorry, we just need, no, we don't need the logging. The logging is already defined. We're going to create new client. I'm going to edit that. So edit message. So what we just need is we're going to create a new logger client and taking a reference to the same logging clone, and we're going to also reuse our on-axis optical model. Where is it defined? Oh, this optical model here. And we use into. So into is useful, but what you lose, what you're passing here is really you create the optical model on the fly, you see, so you don't really have a reference to it to go back. So we're going to define here mute on axis, and we're going to copy optical model here, control, and affect that to that here. Yes, and we have to put it into the proper container in order to be able to use it in an actor. And here we're going to then create the actor with the actor interface. Actor new, and we pass a reference to the client dot clone. And we're giving it the name, and the name is also passed like this. And in that case, we don't need the into. Just like that. I'm going to copy to copy in Slack these two lines that I'm redefining. Okay, so you see what we are doing. We don't really change anything to the model. We're just making sure that the client is not created on the fly. We have a variable which holds it, and we're going to pass a reference to the client, to the actor now. Okay, that makes sense? So now that we have that, we can recreate the optical model actor from the on-axis clone here. And we're going to reuse the timer also. Where is it? I define the timer. When do you define it? Timer. Where do you define the timer? Is it above? Ah, timer here. And here we're going to recreate on the fly because no, I realize I make some. No, I want to create a new logger, so I don't want to reuse the same logger because it's going to the logger here. We're going to have a logger which could have only one step, the last step. So whereas the other one have all the steps. Sorry, so we're going to copy that line. So what I'm going to edit again my thread here. I'm going to modify in Slack also. Voila. Oh, it's messy. What happened? Voila. In Slack, like this we can set and put that here. Voila, like this. Okay. So I redefine a new client, and I will call the file frame here. Or here to be even more obvious, I call last frame. So we have a logger for the last frame. We have an actor. A new actor for the optical model, which reuses the client, and the client, when an actor ceases to exist, the client stays in the state that is that the actor has left it. So when the model ends, the client still exists, and they are in the same state that they were. So that means the client still holds the frame integrated, right? So that's why we're keeping it, and we define a new timer. Okay. So now we're going to put that together. So what we want to do is, and we're going to this timer, I will put one step, but it's not, and then we'll think about that. So now we can do timer dot add output, and we're going to we just need one tick. We just need to trigger the readout now. So we just need one step. And we put that into input, emit the optical model. Okay, so if we do that, timer, yes, if we do that, the timer sends a tick to the optical model, and for the optical model, we're going then now to add the output that we are interested in, which is detector frame. And that goes into the new oh no, it's going to, here it's log because it's a logger. At least it's a bit easy. Log emit logs, and this one is asynchronous, so we go like this. Okay. I think I will try to make sure it build, but it should build. No, what did I forget? Oh, yes, I didn't define a size for this output already, so we need to specify log by changing log to log n, and the size is 512 times 512. And it's just that. Okay. So let's think about that now.
Sorry, could you copy and paste what you have? Because I seem to have a bunch of syntax errors. Thank you.
Yes, don't worry about copying. Just copy and paste, and we're going to think about it. I'll let you do that, and when you have both copy the code, it's compiling now. That's good. There's a warning. Let mute on axis. Well, it doesn't matter. Let's fix that. Okay. I'm going to copy the model here, and I'll put that in Slack also here. Model, we adjust half timer, optical, we don't, not that one, not that one, not that one. Then copy that in Slack as well. Okay, and this we have, and we're going to start to dissect what is happening here. So basically, we create a new model, right? Basically. So everybody has a code in hand? Okay. So let's think about what's happening. So what's happening? So we have oh, I want to change that. JAWS 101. Not knowing. What's happening is so we have a model which have a timer on an optical model, which is already in the state left by the other model. So somewhere there is this integrated frame that we refer, and then the logger. So what's happening is the timer sends a tick, a heartbeat to the optical model, and that trigger, you know, a propagation and a readout of the frame, because then now the detector frame is connected to the logger. So when we write the output, when we write the detector frame output, there's a readout happening, right? That seems okay, except for one thing, that we are, well, what we want to do, we don't want to do propagation here. We just want to do a readout. Okay? And remember, an actor, it's a loop where it reads an input, update where the propagation is done, and write an output. Here we just want to trigger the write, not do the read, not do the propagation. So the way to go about that is to remember the bootstrap option. Sometimes we want, especially when we have a feedback loop, to start with writing an output, not by expecting an input. Do you remember the bootstrap? We have that, you know, it may be simpler if I show that here. You see the integrator here, where it's wider, the line here. It's because we have a feedback loop. So we need at some point, the active optics expect an input first, and then propagate, and then the output. But the input depends on the integrator, which depends on the reconstructor, which depends on the active optics. So you have a loop here. In order to break that, we set on the integrator, on this output, the bootstrap option, which means that when you start, don't start by expecting an input, but just write your default value, which is 0, to the output, right? That makes sense for the bootstrap option here. So we're going to use that here to our advantage in the code. What we're going to say is, okay, we're going to, this output, we're going to flag it as bootstrap. So the first thing is going to happen now is the optical model is going to write this output and send that to the log. So really, no propagation. We directly send that to the log, which is what we want, right? So that's better. And that's what happened to the next step. The timer is going to, which has a step of 1, is going to trigger a propagation for the next step. And we don't want that other. So we're going to set a timer to 0 step. And what happens is that when the timer sees 0, immediately it's going to destroy itself. And you remember when an actor destroys itself, because they're all connected, then the domino effect and they all destroy itself. But because we have bootstrap the detector frame output, the first thing that happens is not to destroy everything, it's sending this output to the log, and then the normal operation resumes, and then everything is cleaned out. You see the trick I'm using here? So it's really based on understanding how the whole actor framework works. But I discover by using it that it's quite flexible. You can play with these properties and create things like that. Does it make sense? There's no feedback. It doesn't sound good.
In order to use this strategy, we probably understood wrong, but when you were saying that thing and putting the timer to 0, the other parts of the simulation that rely on feedback and the normal operation, like let's say like that, are they going to be affected by this tricky? So, I don't know if you understand my question.
Not really. The previous model is not affected. Huh?
Yes, because in that one, the timer is not 0, so it's not going to auto-destroy yourself.
No, and yes, and because you see, at this line 221, the previous timer doesn't exist anymore. It has been gobbled up, chewed, and digested, and it's gone by the model here that we created at line 221. So here we create a completely new actor. Let's look at, you see?
I see.
So the actors are completely new here.
Okay.
Only because they have been passed to the model. So only the client remains in the state that they are after this line.
Sorry, let me explain why I made the confusion. Because I thought that now you have 2 models in the simulation.
Exactly.
And I imagine that you're just replacing. But no, you are creating a new model at the end of the simulation to do all that stuff. Okay, now I understand.
Something else at a different rate, okay?
Okay.
Because what is important to remember is that when a model ends, the state of the client remains. So if you want to do something else with the client, adding them to another model, which goes slower, faster, or something else, you can create a new actor and pass a reference to the same client. You see what I mean? That's why I wanted to illustrate that. And that turned to be very useful. Here is the flowchart of the model we just created. You see, it's very simple. The timer, the on-axis GMT, and the arrow. And we put timer at 0. So the timer starts this loop. He realizes that it has step 0 already. And step 0 for the timer, tell him, because the timer, you say end step, and he's going to discrete the step one by one until it reaches 0. And then you say, okay, that's the end. We stop the simulation there. But we start at 0. So we tell him, okay, the simulation has not started, but you have to already close yourself. And that's going to trigger an event for that one to close itself, and that one to close itself. So if it didn't have the bootstrap, nothing would happen. But because you see this line is wider, that means there's bootstrap. The first thing that has happened, it's also an output from that one which is committed here. And then timer comes in and closes everything. You see?
I see.
I'm not sure if I really understand the original problem that this solves. I thought what I understood is that you have this integrator, but then you take these, when you read it out, you basically reset it. But instead what you want is you want the integration over the whole history.
Yes, over the whole simulation.
But how do you get that without repeating the whole simulation?
Because as I said, the state of the on-axis GMT is preserved. It's not at the end of this first model here. The optical model, which is an actor which contains the on-axis client, is destroyed, but the on-axis client remains available to you with the information contained into it.
Yeah, but do you still have the history, the time history that you're integrating?
So you don't, the client accumulates, so you just want this accumulated value, right? You don't want the time history.
But didn't you reset it during the simulation multiple times?
No, because I commented that out. What I had before was doing that because I was reading the frame, but now that I remove that,
okay.
I don't do that anymore.
I see. So you're rerunning the simulation and you're just not taking the snapshots anymore. And now this is just a trick to get the final value.
Exactly.
Okay, I get it.
Exactly.
Okay.
And it's a bit didactic as well because it shows you it's for me to illustrate you how the dose actors framework work, because you can really use it as your advantage by the fact that you can reuse a client later for another model in the same simulations, and the order of things that happen. The default is really read an output, update your state, and write your output. But you can trick it also by some actors starting them by writing an output, and that's what we're doing. So it's important to have this mental picture of product actors when you build your own model, because you can do a lot of stuff with that. It's quite flexible. So if you look at the previous model that we have, you will notice that on arrow, we don't have the detector frame going on. It's not saved anymore here, because if it's saved, it's a snapshot. It's only for the next model. This one. Here. And now if we go here and we look at so I think I call it logs frame. Oops, no, but like, maybe I think maybe last frame. No, what did last? Yes, last frame, and the data here, the shape. You see, it's only one image, one time step. And if we look at the image now, we start to integrate it.
Could you also have changed how frequently you take a snapshot in the original simulation?
Let me think a minute. No, because you can't, because all the outputs of an actor are the same sampling rate.
Okay.
You cannot do that.
You can change all of them if you want. You can change the integral controller.
Exactly.
You can change everything.
Yes.
But I'm sorry, we have that client that oversamples or downrate the simulation. Couldn't we use that to do it?
So that's a very good question. So let's assume what you're saying and see what's happening. So imagine effectively what Rodrigo is saying is that if we restore the detector frame output here, and we apply a zero-order old sampler that is part of sorry, no, the decimeter. Sorry. So this is which downsample the output. So we have the detector frame coming out, going to another actor, and it's going to take output the detector frame at every 10 samples, for example. Okay, it's what you're saying, Rodrigo.
Yeah.
Okay. Effectively, we will have snapshot every 10 samples, but we don't have integrated because each time you output detector frame, you reset the detector. It triggers the reset of the detector. When you, it's really the model of CEO. When you read the frame, you lose the frame. You don't keep it on the detector. It's destructive reading. That makes sense, Rodrigo, what I'm saying?
But
Yes, it makes sense. I'm trying just to think a way to shade it.
You can't.
Yeah.
You can't.
Okay.
You can't. Each time you read it, you lose it.
But could there be a different implementation of the integrator that doesn't destroy, so it just keeps integrating, but you can still have snapshots?
You could modify CO, but I don't want to do that. I mean, it's the model we have, and
because sometimes you may want to run a simulation and you may want to see the integral developing instead of running the whole thing and then afterwards.
yeah, that's true. But for now, it's not the way it's implemented.
And correct if I'm wrong, I think that the time that it takes to perform this kind of thing, for most of the applications, it should be hard to follow in real time, not in real time, but online what's going on. So in general, we make the batch processing and then we save the information and post-process and analyze the results.
So, but what Christophe is doing is interesting because if we do that, what Rodrigo is saying, no, we cannot do that. I'm thinking what you. Yes, so the only thing we could, if we don't sample all the output, you could have the detector frame and those output are 1/10, for example, the rate of the simulation, right? And that will be saved into the logger. So at the end, if you want to have the full integration, you can sum all the image at the end, and it will be the same. That will work. But here I wanted to show you if you don't want to save intermediate images, just get the last readout, or you do that in that framework. Does that make sense for everybody?
Yeah, yeah. But what in the full end-to-end simulation, we do something where we play with these multiple sample rates. I mean, we are able to update, for example, other subsystems, but we can, using multiple optical models, to sample them in different rates. I mean, we can sample the wavefront 48 by 48, one time in 30 seconds, and we can do faster with the 24 by 24, for example. This is something that we already do, right?
Yes.
Okay.
But this particular case of reading the last frame,
he pushed the wrong button.
Yeah, I think so.
I think, yeah, he's back.
something happened. Okay. Something happened.
We can see you and hear you, Rod. Everything is fine.
And now you can see my screen, I think, too. Okay, so what we are doing, the last readout like this, it's really only way to do it, right? But it's interesting to see that you can recreate a new actors and new model and reusing, if need be, an existing client that has been whereas its state has been updated by the previous model, previous simulation. That's really what I wanted to show you today. Mm-hmm. That makes sense? And the last thing on that topic that I wanted to share is because sometimes, so this is a relatively simple process, but sometimes when you have a first model and a second model, also when you create it, it may take time to create the second model because you may have some calibration or other things to do. So you can benefit from the fact that the model can run asynchronously. Let me show you what I'm doing. So let's define this one, the AO model. And we're going to go, you can oh, so you see what I'm doing here? I'm defining the AO model. So I have to do that way. Let's mute AO model. And then I define a variable and I run it here, right? And then I define the other actors. And before running the last model, then I need to wait for the one which is running. Because you have to wait for him to integrate the frame, obviously. So you see, I remember at some point I was at the question, why do I have all these methods here? It's because you can split them. Yes, I have to do it that way, I think. Our model equal, I think. Yeah, it has to be right in that way. No? Let me see what's the compiler. I've done that in the past, so I must be close, but I must have forget something. Yes, I want to do it that way. Yeah, it's the way to do it. Yes, and then here. Okay, yes, that's what you do. So you can see I define the model until and here I run the model and I save the model here, and then I start preparing my other actors for the next model. And before running this one, I wait for this one to finish. So that means that's useful sometimes when here is very simple, but sometimes I have some occasion where I create another model and take time to create it, so I can have the other one already running in the background. That makes sense? So we have also to remember that the framework is also asynchronous and the model can run asynchronously. So here you can start to run a model and start to do something else. which may take some time, but the model will still run. And then when making sure that you wait at the proper location, of course, when making sure you have everything in the right state. Make sense? Yeah, it works. Okay, I will stop recording here today.
Okay. Will you push this new version in the DOS 101 repository? Okay.
Yeah.